Hello guys, in this video we'll discuss the problems on centrifugal pumps. We'll solve one by one. So we shall take up the problem number 1 now. Problem number 1 says a centrifugal pump is designed to run at 1450 rpm. So let us note down the given data that the speed is 1450 rpm. Next, with the maximum discharge of 18,000 liters per minute. So discharge in the sense it is which is given as 1800 liters per minute. You have to convert this into suitable units as meter cube per second. So how we are going to do it? You know that 1 meter cube is equal to 1000 liters. Okay, and 1 minute equals to 60 seconds. So if you convert it, it would be 0.03 meter cube per second. So immediately convert whenever the value of Q is given in something else. It has to be in meter cube per second. Next, against a total head of 20 meters. So total head in the sense it is nothing but the manometric head which is given as 20 meters. Okay. The suction and delivery pipes is designed in such a way that they are in equal size of 100 mm. So that means both the diameters of suction side and the diameters of the delivery pipe both are same as 100 mm. So I would writing as 0.1 meters. So it is 0.1 meters. Both ds and dd, that is diameter of suction pipe and the diameter of the delivery pipe both are 0.1 meters. And now next, the inner and outer diameter of the impellers are 12 centimeters and 24 centimeters respectively. That means the inner diameter, which is nothing but the value of d1, which is given as 12 centimeters. So immediately convert as 0.12 meters, and the outer diameter d2, which is equal to 0.24 meters. So if we observe in this case, the value of d2 is higher. So if d2 is greater than d1, then you can come to a judgment that it is radially outward flow machine. Okay, so this is radially outward flow. So radially outward flow, nothing but it is a pump, I would say. So if it is reverse, if d1 is greater than d2, then it would be radially inward, where you can observe in case of a Francis turbine, where the problems you have solved in model number 4. Okay, so that one observation you can do from here. Next, so since he has not given anything like whether it is a forward vane or whether it is a backward vane or it is a radial vane at both inlet and outlet, we shall assuming backward vane. Okay, assuming backward vane. So if he has not specified anything in the problem, so you have to assume it as a backward vane. So this you have to remember carefully. Okay, so this particular point is very important. If he has not given anything in the question, so you have to immediately assume it as a backward vane. So as soon as you draw the backward vane, then you draw the velocity triangles of the backward vane. Remember, the outlet velocity triangle for the backward vane is like this, in this order, and inlet for all the three vanes, forward, backward, and this one are same. Okay, so you have to remember all those stuff. Let us go into the solution now. Okay, so solution. Okay, so first we shall first of all, what is asked in the problem? Determine the blade angles beta 1 and beta 2. So what we need to find? To find beta 1 and beta 2 in this particular problem. So we shall try to find those. So from inlet velocity triangle from inlet velocity triangle. Let us operate tan beta 1. So what is tan beta 1 from inlet velocity triangle? So here is tan beta 1. So opposite by adjacent. So this divided by this. So that is what is your tan. So I'll be applying that particular thing now. So that is opposite is Vm1 divided by the adjacent is u1. Okay, so this is what you will get. Now I guess you can calculate the value of u1, which is equal to pi d1 n divided by 60. So what is pi? Pi is constant, pi into 0.12 into speed is 1450 divided by 60. So if you calculate this would come around 9.11 meters per second. So as soon as you calculate that, substitute that. Okay, and even you know that Q is equal to A into V. So I would write it as A1 V1 at the inlet. So A1 is what? Inlet in the sense it is a suction side. So it is pi by 4 d square. D have to take the suction diameter. Okay. So pi ds square by 4. This is the value of A1 cross V1 is nothing but the flow velocity, which is Vm1. So this is an important point here. Okay. So V1 is what? V1 is nothing but the flow velocity, which is Vm1. So from this, what happens, I guess you can calculate the value of Vm1. Since the flow is given, let us substitute all the values. Q is what? 0.03. That is equal to pi into ds is 0.1 whole square into what is Vm1? Vm1 you have to calculate divided by 4. So if you calculate this stuff, the value of Vm1 would be 3.82 meters per second. Now since you have got the value of U1 and Vm1, you can calculate what is beta 1. So beta 1 would be the tan inverse of Vm1 divided by U1. So that is equal to the tan inverse of Vm1 is how much? 3.82 divided by U1 is 9.11. So from this, the value of beta 1 is equal to 22.7 degrees. Okay. Next. Now we shall go with beta 2. So where is beta 2? So here is the value of beta 2, if you observe. And this one is straight. Okay. So now here is the value of beta 2. So opposite is this and adjacent is this. So opposite is nothing but the whole value of Vm2. What about the adjacent? dE, which is U2 minus of Vu2. I will just operate the same thing here. Now from outlet velocity triangle, beta 2 is equal to tan inverse of, I will write directly, it is tan inverse of Vm2 divided by U2 minus of Vu2. Okay. Next. I guess you can calculate the value of U2. Easy. So it is pi d2 n divided by 60. That is equal to pi 0.24 into 1450 divided by 60. So from this, the value of U2 is 18.22 meters per second. Okay, so this is how you calculate the value of U2. Now, as flow velocity as the flow velocity remains constant, what you can infer is Vm1 would be equal to Vm2. Since you have calculated the value of Vm1 as 3.82, and that would be also Vm2 would be also 3.82 as well. So Vm2 is equal to 3.82 meters per second. Okay, even that is also there. So Vm you have known, U2 you have known. I guess you have to know the value of Vu2 now. So for that, we will be having the manometric head is equal to U2 Vu2 divided by G. And always note, okay, we know that this is, and kindly note that the value of U2 Vu2 divided by G is called as Euler's head. Okay, and this particular Euler's head plus friction head would be equal to the manometric head. Hence, under the absence of friction, we can consider that Euler's head would be equal to manometric head. Okay, when under the absence of friction. That is why I have taken here directly HM as equal to U2 du2 divided by G. I guess he has given the value of HM in the problem as 20, and U2 you have calculated it as 18.22. Vu2 you have to calculate now, divided by G is nothing but 9.81. So from this, the value of Vu2 would be 10.76 meters per second. So now I guess all the three values are known in that particular equation, which says beta 2 is equals to tan inverse of Vm2 divided by U2 minus of Vu2. All the three parameters are known. Just substitute now. Tan inverse of Vm2 is how much? So it is 3.82 divided by 18.22 minus 10.76. So that is equal to beta 2, which is equal to 27.1. So since you have calculated the values of beta 1 and beta 2, so just write the result statement at the end. Do not forget to write a result statement and each and every problem, whatever you attend in your examination, just write the blade angles at inlet and outlet of given pump were calculated as 22.7 degrees and 27.1 degrees respectively. So after you write a result statement, you can end your problem.